So in this problem, we want to find the absolute minimum and absolute maximum of a function. So it says, suppose f of xy equals 5x plus 5y, at which negative 5 is less than or equal to x is less than or equal to 5, so x is between negative 5 and 5, and negative 5 is less than or equal to y is less than or equal to 5, so y is between negative 5 and 5. So what that's doing is it's defining for us a rectangle, actually a square, in the xy plane. So let's just draw a picture of that. We're going from minus 5 to 5 in the x and minus 5 to 5 in the y. So we're looking at all the points inside this square, and we're trying to find out at which of these points is this function the smallest, and at which of these points is this function the largest. Okay, so the first thing you want to do is you want to investigate the interior of this square. You want to find out, could the function be the smallest on the inside? Well, if that's the case, that's going to be where the function has a local minimum or a local maximum, right? So to find that, we need to find where the gradient of the function is equal to 0. So let's compute the gradient of f here. Gradient of f is the x derivative, which is just 5 in this case, and the y derivative, which is 5 in this case. So where is that equal to 0? Well, never. It never equals 0. That's impossible. This is always the vector 5, 5. It can never be the 0 vector. Can never be the 0 vector. So that means that there are no local mins or maxes inside this square, which means that the only place a maximum or minimum could occur is actually on the boundary. So really, all we have to do for this problem is explore the boundary of this square. Okay, well, if you look at this, it has corners, right? And so you can break this boundary into 4 parts, one part representing each one of these lines. So let's see. Let's take this line here. Let's take this line right here. How do we describe this line? Well, that's the set of points whose x-coordinate is equal to 5. And, well, the y-coordinate is just between negative 5 and 5. So that's what that line is. So I just want to look at the function under these conditions. So what I'm going to do is in the function, I'm going to replace x with 5, and I'm going to look at the resulting function over this interval, viewing it as a function of the only variable that's left, which is y. So, okay, if I go back to my function here and I replace x with 5, so let me write this. On the right border of our box, f is just equal to, well, x has become 5, so it's just 25 plus 5y. And we want to find where this is the smallest and where this is the biggest. Well, this is a single variable calculus problem because this is a function of a single variable, only y, and we're minimizing it or maximizing it over an interval. So you know how to do that. You find where the derivative is 0 or undefined, so we'll compute the derivative of f. Well, that's just equal to 5. Well, that's not 0 or undefined anywhere, right? Not 0, nor is it undefined anywhere. So there are no critical points, or I like to call them critical numbers, actually. There are no critical numbers where numbers for y where this would be 0 or undefined. So the only place that it could be, where it could have a maximum or minimum on this interval is at the endpoints of the interval. So check the value of f at the endpoints. So at y equals negative 5, we have f is equal to 25 plus 5 times negative 5, well, that's 0. And at y equals positive 5, f is equal to 25 plus 5 times 5, which is equal to 50. So it's the smallest when y is negative 5, so that's over here. That's where it's the smallest. So let's just write f equals 0 there. And it's the biggest over here. That's when y is 5, and that's when f equals 50 right there. Okay? So that was the right border. Now let's check the top boundary of this square. On the top border, well, what's going on the top? Before I write down my equation here. On the top, now here y is fixed equal to 5, and x is between negative 5 and 5. Right? So I'm just going to write down f with those conditions in place. So y is equal to 5, and x is varying. So my function looks like this. So we want to minimize or maximize this on the interval from negative 5 to 5. Well, so what we do is we find the critical numbers, and we do that by checking the derivative. The derivative is 5, so there's no critical numbers. Okay, so the only place it can have a minimum or a maximum is at the endpoints. So we check the endpoints. At x equals negative 5, what do we have here? Well, we have f equals 5 times negative 5 plus 25. That's 0. And at x equals positive 5, f is equal to is equal to 5 times 5 plus 25. That's equal to 50. Okay, so that's what we got. Let's label that on our picture. All right, so let's see. When x was negative 5, it's 0. When x is positive 5, it's 50. So we already had this one, right? Maybe I didn't even have to do that over again, the 50. But now we know that at this corner, f is equal to 0. Okay, now let's do the left boundary. You just keep going for every boundary here. So I'll do these other ones pretty quickly. On the left, f is equal to, well, now x is negative 5, right? So it's going to be negative 25 plus 5y. There are no critical numbers, so we just look at y equals negative 5. F is equal to, if you plug negative 5 in for y, you get negative 50. And at y equals positive 5, f is equal to 0. All right. So on the left, when y was negative 5, we found out that f was equal to negative 50. Right. And when at y was 5, we get f equals 0. Now we should just investigate this bottom piece because it might have a minimum in the middle. All right, we know its values on the endpoint, so we don't need to check those, but we should check to just make sure it doesn't have a minimum in the middle. So let's just quickly do that. On the bottom, well, what's going on the bottom? Well, y is equal to negative 5. So I'm just going to replace y with negative 5 in the expression for f. So f looks like this. Does it have any critical points? Well, no, because the derivative is 5. So there's no critical numbers here. So it doesn't have a minimum or a maximum in the middle here. And we already determined the values on the boundaries in the previous parts of this problem, so we're done. And we can see that the biggest the function gets is at this point right here, and it has value 50. And the smallest the function gets is at this point right here, where it has value negative 50. So if I write my answers in here, the absolute minimum of the function is negative 50. The absolute maximum of the function is positive 50.